So we start with chapter 1 from the book. And in this chapter, before doing any algebra, we revisit some arithmetic. To start with, we introduce a notation Z, this semi-bold Z, stands for the set of integers. We mean all integers, positive and negatives. So this is 0 plus or minus 1 plus and minus 2 and all others. We will investigate properties of Z and prove some properties at the same time, proving properties of integers. We're going to start with something, so some properties are going to be taken for granted. A natural question is whether we are really going to do all that very rigorously, and the answer is no, not in this class. A rigorous theory of integers, rigorous arithmetics may be done in foundation law of mathematics logic class. There you will learn about Zermelo-Fraenkel system of axioms and how various properties of integers can be derived from these basic axioms or other systems of axioms. So our approach is a little bit different, and it is predetermined with our goal. Why at all? We're going to prove some properties of integers which actually we know as experimental facts, or you can really take for granted. At least we need to take some properties for granted. Why not take all of them for granted and go? After all, you probably do not have any doubts that these properties, all of them, those which we take as basics, do not prove, and those which we really starve to prove, all these properties are really true. The point is actually different and as follows. We prove something here in this chapter at least, not because we have any doubts that these facts are true. Later on in this class, we will meet other objects which we'll call rings. And they are in a sense similar to the set of integers which with its operations of addition and multiplication. We will then need to prove certain properties of those objects. In order to do that, we first see how to derive some properties of integers out of some basic properties of integers. We concentrate not on proving well-known facts, but on the arguments itself in order to later apply this same or similar argument in a different situation. Here are some examples of properties of integers, numbers, which we will take for granted. First of all, what are the basics which we are not going to prove? Properties of integers taken for granted. Here is a, b for two integers a and b equals 0. The product is 0 implies a is 0 or b is 0. Or both. Implies that at least one of them must be 0. Another one, also taken for granted, is if an integer b is not 0, then a by absolute value is smaller equal, never exceeds ab. And then what I say here, or this is the same thing as absolute value of a times absolute value of b. Or what I say here, if we multiply a positive integer by another integer, we get something at least as big, another positive integer, we get something at least as big as the original positive integer itself. All non-zero integer positive integers are at least 1 by their size. Notation which we use, the absolute value, is of course negative x if x is negative, or x if x is non-negative. Here is a less common and less obvious property which we also take for granted, and it probably requires some comments. These two examples are just obvious facts, well known, and we take them as obvious, well known facts. Less common example is the well-ordering axiom. Well-ordering axiom. That axiom tells us that every non-empty set of non-negative integers contains its smallest element. one can reformulate that using some notations. Here is a reformulation. We denote by n the set of non-negative integers. This is integers which are bigger or equal than 0. And with this notation, we say f s is a subset of n, and S is not the empty set, then there exists an element M in S such that for every X in S, we have that M does not exceed X. M is the smallest element, so every non-empty set has the smallest element. That is really an obvious fact. If you think for a minute, you understand that, yes, you know about that. What you probably do not know, that here are some remarks about well ordering axiom. First of all, this property is equivalent to the principle of mathematical induction. So, well ordering axiom is equivalent to what you typically call the principle of mathematical induction. In fact, this equivalence is not at all something difficult. You can prove it on your own, one, or if you're interested, you can look up in the book. There is Appendix C. And you can look up some details about this equivalence there. Secondly, one can restate that not only this non-empty subset of that, or not only that, you can restate it as just every bounded below subset of integers not only subset of positive integers, but just some reformulations, restatement. Every bounded below subset of integers as the minimum, smallest element. Or I'm going to say about same thing about bounded above. So you may also say same thing. Instead of below, you can say above. And now it's going to be the biggest element. It is bounded, say, bounded above, as an example, or if you take the set of all the integers positive or negative, which are smaller than 100. Or you actually don't know that this is all smaller than 100, some subset, some set of integers which you know are all smaller than 100. Of course, there should be the biggest element there. And this is very clear how to find it. You look at the 100, you know they are all smaller than 100. 100 itself may be not the biggest element simply because 100 is not necessarily one of them. All right, go down to 99. 100 was not one of them. They all do not exceed 99. Are they gay? Is 99 one of them? Yes, then this is the biggest element. No, go step down, 98. Is 98 one of them? It is still bigger than every one because 100 and they are all smaller than 100. 100 is not there, 99 is not there. Next candidate is 98. If 98 is not a member, go down to 97 and continue. The fact that, oh, I forgot to say, bounded below and above, in both cases, the subset should be non-empty. That's very important because the process I just described may never stop for an empty set, and clearly empty set doesn't have a smallest element, empty set doesn't have a biggest element. For a very good reason, empty set doesn't have elements at all. If your set was non-empty, sooner or later you will be going down the process I've just described from 100 downstairs. Sooner or later you find an element, and that's gonna be the biggest element of your set. So all these three formulations are equivalent, and all of them are equivalent to the principle of mathematical induction. Our ability to make a proof by induction. This is what principle of mathematical induction means. What does it mean? The principle of mathematical induction. That's It is allowed to make an argument using mathematical induction. As soon as it is allowed to make such an argument, the well-ordering principle is true for integers. And other way around, if well-ordering principle is true for integers, then that is the reason we can make arguments using mathematical induction. And another remark about well-ordering axiom is that well-ordering axiom is true for integers but not for everything. Or maybe not just, for something else as well, just not for everything. It's true for Z, not for everything. For example, the axiom is not is false for Q, the set of rational numbers. Also false for reals. In the same way, what happens with rationals? The set of all positive rational numbers. Positive rationals does not have a minimum element. The reason is very simple. It would be 0, but 0 is not here. We take only positive integers, rationals. If we took non-negatives, it would have its smallest element, but now it doesn't. For every element, any element in this set, we have that r over 2, half the element, is also the element of the same set. And clearly, r over 2 is smaller than r. Thus, no element is the smallest. In contrast, for integers, similar set, non-negative integers has its smallest element one, as the smallest element. That is all about the properties of integers which we take for granted. Some very simple properties, you know pretty well, and well-ordering axiom. Now, what we are going to prove, our goal in chapter 1, what kind of arithmetic we are going to discuss. So our goal as the fundamental theorem of arithmetic. Theorem which, with that prouder name, is actually also a well-known fact. This is theorem 1.8 in the book, which roughly says that every integer except zero and plus or minus 1 can be represented as a product of primes. In an essentially unique way. Essentially means that 6 is 2 times 3 or 3 times 2, and this is the same product of primes after permutation, some small tinkering with signs. This is unique. You most probably know this fact, and this fact was considered something to prove long ago. It was realized that this should not be taken as an experimental observation, but should be proved out of simpler properties of integers. That happened more than 2,000 years ago. Euclid actually knew that this fact requires a proof and knew how to prove that. Again, our goal is to prove this theorem not because there are any doubts that the theorem is true, but because we want to revise Euclid's argument in order to, after that, apply this one or a similar argument to objects other than integers.